Emission. An emission nebula is a cloud of ionized gas that produces its own light. A nearby hot star, usually a young massive one, radiates ultraviolet energy intense enough to strip electrons from surrounding hydrogen atoms. When those electrons recombine with their atoms, they release photons. The dominant color is red, produced by hydrogen alpha emission at 656 nanometers. These are the birthplaces of new stars. The gas and dust inside them collapse under gravity over millions of years until enough pressure builds at the center to ignite fusion. Reflection. A reflection nebula does not emit its own light. It is a cloud of dust that scatters starlight from a nearby source. The dust particles scatter shorter wavelengths more efficiently than longer ones, so reflection nebulae appear blue, the same mechanism that makes Earth's sky blue. They require a star close enough to illuminate them, but not hot enough to ionize the gas. Without that nearby star, they would be invisible against the background of space. Dark. A dark nebula is a cold, dense molecular cloud with no internal light source and no nearby star bright enough to illuminate it. It is detectable only as a silhouette against a brighter background, blocking the stars or glowing gas behind it. Temperatures inside can drop to 10 degrees above absolute zero. The cloud is made mostly of molecular hydrogen, dust, and complex organic molecules. These are the conditions new stars require. The cold slows molecular motion enough for gravity to pull matter inward and begin the collapse toward fusion. Giant molecular cloud. A giant molecular cloud is a cold, dense mass of gas and dust on a scale that dwarfs individual nebulae. They can contain from 10,000 to 10 million solar masses of material and span hundreds of light years. Nearly all star formation in galaxies occurs inside them. Individual dark nebulae, emission nebulae, and reflection nebulae are typically embedded within or on the edges of giant molecular clouds. When a shock wave from a nearby supernova or the gravitational pull of a spiral arm compresses a region inside one, star formation begins. The Milky Way contains several thousand of them. Planetary. A planetary nebula is the ejected outer shell of a dying star between 1 and 8 solar masses. As the star exhausts its fuel, it expands into a red giant and begins shedding its envelope over thousands of years. The exposed core, now a hot white dwarf, emits ultraviolet radiation that ionizes the surrounding material and causes it to glow. The resulting structures are often symmetric, ranging from spherical to bipolar, depending on the rotation and magnetic field of the original star. The nebula disperses into the interstellar medium in roughly 20,000 years. The white dwarf remains, cooling indefinitely. Protoplanetary. A protoplanetary nebula exists in the brief interval between a dying star shedding its outer envelope and the exposed core becoming hot enough to ionize the surrounding gas. Without ionizing radiation, the shell is visible only in reflected light or infrared. The phase lasts a few thousand years at most, which is why only a small number have been identified. Their shapes are often bipolar or irregular, pushed into asymmetry by fast stellar winds beginning to emerge from the central star before it fully heats up. Once the core reaches around 30,000 Kelvin, the surrounding gas begins to glow and the object becomes a planetary nebula. Bipolar. A bipolar nebula has two symmetric lobes separated by a narrow waist, producing a shape that resembles an hourglass or butterfly. The structure forms when a dying star sheds material faster along its equatorial plane than along its poles, often because a binary companion, or a dense disk of gas, constrains the outflow. Material escaping through the poles expands freely and inflates the two lobes. Some bipolar nebulae are planetary nebulae caught in an extreme form of asymmetric shaping. Others form during the protoplanetary phase, where the bipolar structure appears before the central star is hot enough to ionize anything. Supernova Remnant. A supernova remnant is the expanding debris shell left after a massive star explodes. The explosion drives a shockwave outward at thousands of kilometers per second. Where it collides with surrounding interstellar gas, it heats that material to millions of degrees, causing it to emit X-rays and visible light. The shell decelerates as it sweeps up ambient matter, and after tens of thousands of years, it merges with the interstellar medium. The heavy elements it carries, forged in the interior of the original star, become the raw material for future stellar and planetary systems. Pulsar Wind. A pulsar wind nebula is powered not by an explosion, but by a rapidly spinning neutron star continuously injecting energy into surrounding gas. The pulsar drives a wind of electrons and positrons outward at near light speed. Where this wind meets the surrounding medium, a termination shock forms and the particles slow, creating a bright glowing region that sits inside or alongside the outer Supernova Remnant shell. The Crab Nebula contains one of the most studied examples. The pulsar at its center formed in a supernova observed in the year 1054, and it still powers the inner nebula today at 30 pulses per second. Nova Remnant. A nova remnant is the expanding shell of gas ejected when a white dwarf in a binary system explodes on its surface. The white dwarf pulls hydrogen from a companion star until the accumulated layer is dense and hot enough to trigger a runaway thermonuclear reaction. The explosion is violent but leaves the white dwarf intact. The ejected shell expands outward and becomes visible as a faint, glowing ring. Unlike a supernova remnant, the system survives. The process can repeat if the white dwarf continues to accrete material, producing what is called a recurrent nova. Wolf-Rayet. A Wolf-Rayet nebula surrounds a Wolf-Rayet star, a massive, extremely hot star losing mass at a rate millions of times greater than the Sun. The powerful stellar wind, moving at several thousand kilometers per second, sweeps up and compresses the gas the star shed during its earlier red supergiant phase. The compressed shell glows under intense ultraviolet radiation from the central star. Wolf-Rayet stars are near the end of their lives. When one explodes as a supernova or collapses directly into a black hole, the surrounding nebula becomes a supernova remnant. The entire Wolf-Rayet phase may last only a few 100,000 years. Cometary. A cometary nebula is shaped like a comet, with a bright head and a fainter tail pointing away from a nearby star. The structure forms around a young stellar object still embedded in its birth cloud. Radiation pressure and stellar winds from the young star push the surrounding gas away, creating the tail. The head, directly facing the star, is denser and more illuminated. Most cometary nebulae are reflection nebulae, scattering starlight rather than emitting it. They represent an early phase of the relationship between a newborn star and the material it formed from, before the star disperses its surrounding cloud entirely. Herbig-Haro Object. A Herbig-Haro object is a bright patch of nebulosity produced when jets of gas from a newly forming star collide with surrounding interstellar material at high speed. The jets are driven by magnetic fields near the protostar's accretion disk and travel outward in two narrow columns in opposite directions. Where they meet the interstellar medium, shockwaves heat the gas and cause it to glow. As the protostar evolves and the jet weakens, the object fades. Individual Herbig-Haro objects can change shape or disappear on timescales of years, making them among the most visibly dynamic structures in the sky. Thanks for watching. If you could watch any one of these up close, which would it be? Let me know in the comments. Also, please remember to like and subscribe if you enjoyed this video.